Light, this is chapter 8. And so I need to talk a little bit about light first. Light is also called electromagnetic radiation. Electromagnetic radiation. It's energy. There's energy in the form of light. And what light is, it consists of oscillating electric fields and oscillating magnetic fields. So an oscillating field just means in one instant it's positive and in the next instant it's negative. So we just oscillate between positive and negative. Positive and negative. That's the electro part of radiation. The magnetic part is perpendicular to the electric field. We have a magnetic field. The magnetic field is going to have north pole, south pole, north pole. This is going to be oscillating north-south pole. And this is traveling. It's not a standing wave. It's traveling. That is, it's traveling very fast, actually. This is traveling at the speed of light. And the speed of light is 3.00. This is just a 3 sig figs. It's like 2.99 something times 10 to the 8 meters per second. And so light moves extremely fast, much faster than sound. So we have the oscillating electric field. And then we have this oscillating magnetic field. So we aren't going to do too much with the magnetic field, but light's going to interact with matter. So for example, if I'm a little magnet and this is moving at me, then what I'm going to see is let's say, south pole. So my magnet might flip. So it's north pole and south pole is an attraction. Opposite poles attract. Then I see north pole, and then the magnet flips again. And so an oscillating field, the magnetic field, will cause the magnet to flip back and forth, between one orientation and the other. Oscillating electric field will do the same thing. So for example, if I'm an electron, electrons are negatively charged, so if I see negative, it's going to be repelled. If I see positive, it'll be attracted. So what happens with an oscillating electric field is it's going to interact with the electron, and it's going to cause the electron to oscillate as well. Oscillating magnetic fields are important in chemistry as well, because electrons, although they don't look it, they have a north pole and a south pole. And so electrons are little magnets. The magnetic field can interact with the electron as well. But not just electrons. The nuclei, a lot of nuclei are also little magnets, like the hydrogen nucleus, the proton. The proton acts like a little magnet as well. So it's going to have a north pole and a south pole. And so it can interact with the oscillating magnetic field. And so that gives rise to certain techniques like nuclear magnetic resonance or magnetic resonance imaging. Magnetic resonance imaging takes advantage of these little magnets in hydrogen atoms, the nuclei, and then flips the spins. We call it flipping spins. But what we're going to focus on is the electric field component and how it interacts with electrons. Not only will it interact with electrons, it will interact with bonds as well. So if I have a polar bond like this, a polar bond is going to have a positive end and a negative end. And so here, this would be an alcohol bond, and the hydrogen would be positive and the oxygen would be negative. And so when we have an oscillating electric field, what that does is it causes the bond to vibrate. The electrons will just oscillate with the field, bonds will vibrate with the field. And so interact with charge. All right. So there are certain things that we should know about electromagnetic radiation. Let's take a look at these. This is the first part of Chapter 8. The first part, Chapter 8 is electrons and atoms. The first part deals with electromagnetic radiation, which interacts with electrons. Here's a traveling wave here. One of the characteristics of a traveling wave, there are a number of things, is the wavelength, which is lambda. So when we have a wave like this, we want to know the peak-to-peak or the valley-to-valley distance. The peak-to-peak distance is lambda, which is going to be the same as the valley-to-valley distance. This would be lambda. And so we call this one wavelength here. That is, if we go from the top down back to the top, as this is traveling to us, this is traveling at the speed of light. Do you know the symbol for speed of light? C. C is the symbol that we use for speed of light. So this is traveling at us at the speed of light. And so one up and down, or down and up and down, one of those cycles is one wavelength. So lambda's wavelength. And it depends on the wavelength. If the wavelength is very long and it's traveling to us, then the cycle is slow. That is, we start up, drop down, come back up. That's one cycle. That is slow, meaning it takes a little bit longer. If the wavelength is very short, then the cycle happens very quick. So it's up, we start up, down, up, versus up, down, up, And so that would be frequency. Frequency is the number of cycles per second that hits. So if we're over here at the detector, we're going to see we're up, down, up. That's one cycle. How many of those cycles happen in a second? That's our frequency. Frequency is given the symbol nu. And the units for nu are in hertz. And 1 hertz is 1 up and down or 1 up and down and up type cycle per second. And so if I had a frequency of 1 hertz, then in 1 second, I'd go through 1 complete cycle at 1 wavelength of this. That would be 1 hertz. 1,000 hertz, I'd have 1,000 cycles in 1 second. Oftentimes, we leave off the cycles and just call it seconds to the -1. It's actually a cycle per second, but units would just be seconds to the -1. The typical units for wavelength are in meters. Speed of light is in meters per second. And so we can come up with this equation here. And that is C is equal to lambda times nu. The speed of light is equal to the wavelength times the frequency. Or the frequency is equal to C over lambda. And so frequency and wavelength are inversely proportional. The smaller the wavelength, the higher the frequency. And the longer the wavelength, the lower the frequency. Okay, there's one more thing we should know, and that's amplitude. Amplitude is how big is the wave. Amplitude. The larger the wave, the greater the amplitude. Amplitude is related to energy. Energy of light is a bit tricky. Energy of light is related to the amplitude. That is, the higher the amplitude is also called intensity. The more intense the light is, the more energy. That is, the brighter the light bulb, the greater the intensity, the greater the amplitude of the light, the greater the energy. And so energy of light is related to the amplitude. And in classical physics, that's it. When the physicists look at this is what they predict. The energy of light is going to be based on how big the amplitude is. But it turns out that it's a bit more complicated than that. And so here's the diagram here showing the oscillating electric field and the oscillating magnetic field. They're perpendicular, and so they're shown as planes here. They're showing different wavelengths here. Long wavelength on the top, short wavelength on the bottom. Long wavelength is lower frequency, short wavelength is higher frequency. They both move at the same speed though. And so long wavelength moves at exactly the same speed as short wavelength in a vacuum. However, in other media, they might not move at the same speed. So this is the SI unit for frequency is the hertz, abbreviated Hz, cycles per second. Wavelength is typically in meters, but sometimes it's not so convenient. So we see wavelengths on the order of centimeters, millimeters, micrometers, nanometers, angstroms, picometers. Those are all common units for wavelength. Here's the equation relating mu and lambda. The speed of light, if you wanted to more sig figs, this would be at 2.99792458 times 10 to the 8 meters per second in a vacuum. But most people will just round it to 3.00 times 10 to the 8. I used to know this to 4 sig figs, 2.998 times 10 to the 8, because I like to have my constants to 4 sig figs to minimize rounding error. And so either use 2.998 or 3.00. Okay, we're going to skip this for right now. We're going to be talking about the energy of light. Continue talking. So something was missing from the physics here. It wasn't just the amplitude. This is classical physics. And so some modifications had to be made in classical physics. And those modifications resulted in quantum physics. And so what are these modifications, or how do we think of in terms of these waves? Now, this is best illustrated with the photoelectric effect. The photoelectric effect is when light strikes the surface of certain metals, electrons are ejected. So some metals have very loosely held electrons, like potassium metal. Potassium metal is a great reducing agent. That means something can come along and take the electrons easily. And so if we have an oxidizer can come over and pull the electrons off potassium atoms without too much difficulty. But not only can we knock or remove electrons off potassium with an oxidizer, we can also shine light on this. So let's shine, let's say, 10 watts of green light. Now, watt is a unit of power. And so 1 watt is defined as a joule per second. And so joules worth of energy in 1 second. And so here we have 10 joules worth of energy in 1 second. And so that's 10 watts of green light. And when I shine 10 watts of green light, what happens here is electrons get ejected off the surface. That's enough to knock electrons off. In other words, one way of thinking about this is this. 10 watts of green light, that green light knocks an electron off. It excites it, we say. So what if I use 10 watts of red light? Same amount of energy. Same amount of energy, so it should have the same effect. I'm putting 10 joules worth of energy on the surface of this. And so if I do 10 watts of red light, you would expect it to be ejected, but it's not. In fact, 10 watts of red light does nothing to this. And so energy is a little bit more tricky. This 10 watts, this is the total energy or the power. Which is proportional to the amplitude or the intensity. And so we have the same total energy here. So what we do then is, let's go to 100 watts of red light. It's 10 times more energy here. So it'd be much more intense. So we'll go with 100 watts of red light. It's 10 times more energy. What do you think? Well, what happens here is, again, no electrons are ejected. It's going to get hotter, probably, but we aren't going to see any electrons being ejected here. Let's go to 1,000 watts. If we go up to 1,000 watts, which is 100 times more energy than 10 watts over there, do we see any electrons being ejected? No. And so this is it. Here we have a red light, 10 watts would be like this. Here the amplitude's 10 times bigger than that. And here the amplitude's 100 times bigger. This is like a huge tidal wave. Surely this huge tidal wave of red light should knock electrons off, wouldn't you think? And it turns out, no, it doesn't. And so there's something else involved. It's going to get very hot, and 1,000 watts of red light will probably melt potassium. You know, it'll melt it because the electrons do get excited, but they don't get knocked off. They don't get ionized. And so it's not enough to ionize it. And so 1,000 watts of red light won't do it. And so this is called the photoelectric effect. The photoelectric effect is shining light on the metal and knocking electrons off. The electrons emitted through this process are called photoelectrons. So the salient feature of the photoelectric effect is that the electron emission only occurs when the frequency of the incident light exceeds a particular threshold value. When this condition is met, the number of electrons emitted depends on the intensity of the incident light. So green light is not electrons. So if I make it more intense, I'm going to knock more electrons off. So 100 watts of green light will have a lot more electrons being ejected. The kinetic energies of the emitted electrons depend on the frequency of the light. And it turns out if I go to higher frequencies of light, then the electrons get emitted with more kinetic energy, with more speed. And so in other words, the frequency of the light or the wavelength of the light is going to have an impact on the energy. These observations, especially the dependence on frequency, could not be explained by classical wave theory. So this couldn't be explained by classical physics. And therefore, modifications had to be made to classical physics or classical wave theory in this case. However, Albert Einstein showed that they are exactly what would be expected with a particle interpretation of radiation. And so one way of thinking about this is, okay, if we have a tidal wave here hitting this, and the tidal wave consists of ping pong balls, if you had a tidal wave of ping pong balls, would you worry so much? No, I mean, if you got hit by a tidal, even if it is a tidal wave, even though there's a huge number of ping pong balls, it's not going to cause enough damage. However, over here, we would have something like bowling balls instead of ping pong balls. So these balls would pack a lot more punch. There'd be fewer of them, but these would be like bowling balls or bullets or something. And so one bowling ball is enough. One ping pong is not enough. A billion ping pongs aren't enough. Even though the cumulative energy here might equal the single energy of a bowling ball. In fact, the cumulative energy here can exceed that. And so we could have way more energy here, which is the total energy, which we do, 1,000 watts, versus over here, which is only 10 watts. But it still won't do it, because each ping pong ball doesn't have enough punch to knock an electron off. And so what size, or, in other words, this is like the particle interpretation of the light. And so when we think about light, light consists of particles, but these aren't literal particles. Normally particles are going to have mass and take up space. These particles have no rest mass. And so particles may not be the best word for this. Some people call this a packet of light. And so the light comes in little packets. It's not. So when we're thinking about amplitude, it's not just the amplitude. We have to look at the individual packets. And the individual packets here can be small or they can be large. It turns out the longer the wavelength, the lower the frequency, the smaller the packets. The shorter the wavelength, the higher the frequency, the bigger the packets. And so this is going to contain much larger packets, just fewer of them, but each one of them are going to pack more punch. And the energy of these packets, which we call, these packets are photons. photon is a particle of light, but not a literal particle. So the energy of the photon is going to equal h, which is a constant, times the frequency, mu, or hc over lambda. H is something we call Planck's constant. Planck's constant. Usually people learn Planck's constant to 4 sig figs. Actually, you don't have to memorize it. It's 6.626 times 10 to the minus 34 joules times seconds. So this is the energy of a packet of light or a photon of light. The energy is equal to h nu, which is equal to hc over lambda. So the energy is directly proportional to the frequency. The higher the frequency, the greater the energy. And it's inversely proportional to lambda. So the longer the wavelength, that is, the larger the lambda, the lower the energy. This is Planck's constant to 6 sig figs, 6.62607 times 10 to the minus 34. The units for Planck's constant are unusual. It's joules times seconds. You know, what was a joule per second? A joule per second is called a what? It's called a what? A joule per second is a watt. So what is a joules times a second called? Well, joule per second is a watt. A joules times a second is not a watt. There's actually no name for it. It's called a unit of action. Joule per second is a unit of power. Joules times second is a unit of action. It's kind of a weird unit. So this is the photoelectric effect. Photoelectric effect just says that there are two energies you need to pay attention to. There's the total energy and the photon energy. And so we always think in terms of total energy and photon energy. The photon energy is the energy of a packet of light or a particle of light that's equal to h nu, which is equal to hc over lambda. And so we could have just one photon or we could have a bunch of photons. And therefore, we're going to have the total energy. The total energy is going to equal the sum of the photon energy. The more photons we have, the more intense the light is. In other words, the brighter the light and the higher the amplitude. And so the total energy is directly proportional to the amplitude. And so, yes, the amplitude is important. That is the intensity, whether it's a dim red light or a bright red light. But then we have to think in terms of red light turns out to have a lower photon energy than green light. Green light has a higher photon energy. And so we'll take a look. Like this. So this is electromagnetic spectrum, and we can see here, we start off with long wavelength, low frequency. Long wavelength, low frequency. Frequency is at the top here. And then we go from long wavelength, low frequency. Long wavelength, low frequency is low energy. And then we can go, you know, the higher the frequency, the shorter the wavelength, the higher the energy. So radio waves have the lowest energy. of the electromagnetic spectrum. And radio waves we can't see, they're invisible. And then a little higher in energy than radio waves are microwaves. And then higher in energy than microwaves is infrared. And then we have this little thing here. This is visible. Visible is a very small part of the electromagnetic spectrum, but it's the part we can see. And so then from infrared, we have visible light. The first color we encounter with visible light is red, and then orange, and then yellow, green, blue, indigo, violet. And so we have this Roy G. Biv, from low energy, long wavelength, low frequency, to high energy. And so we can see here that green photons will pack a lot more punch than red photons. Red photons being longer wavelength, lower energy photons. Green photons are shorter wavelength, higher energy photons. And so if green photons were enough to ionize potassium, will blue photons do it? Yeah. Indigo, violet will do it as well. And so those will ionize it. How about infrared photons? Will infrared photons ionize potassium? No. Infrared doesn't have enough punch. What if I did this? What if I did 1,000 watts of infrared versus 0.1 watts of green? 1,000 watts versus 0.1 watts. 1,000 watts is a lot more energy, right? So will 1,000 watts of infrared do it? Ionize it? No, not at all. And so those are the two energies we have to think of. And so another way of thinking about this is, okay, after violet comes, and then gamma rays. So what would you rather be hit with? Would you rather be hit with 100 watts of red light or 0.1 watts of X-rays? 100 watts of red light or 0.1 watts of X-ray? 100 watts of red light. What would you rather be hit with? 1 watt of red light or 1 watt of gamma rays? Yeah, some people might say they're the same. 1 watt is 1 joule per second. So if I get hit by 1 joule per second of gamma radiation versus 1 joule per second of red light, it's the same thing, isn't it? Is it the same thing? No, it's not the same. It's not the same. You got to be careful because some people, the way they understand energy is different. So, for example, I was listening to this thing about Fukushima. Did you know the meltdown they had there? And this person was calculating the radiation dosage. Well, the thing was, he took that radiation and spread it over the entire body. So if you take 1 gamma ray photon and then take that energy and spread it over the entire body, is that very much energy? No, it's barely any energy. But the argument there was, okay, you spread it across, it's barely any energy, so it's nothing to worry about. Is that correct? Gamma radiation is nothing to worry about because if you're exposed to very, very little gamma radiation, the total energy is very small. And if the total energy is very small, it can't cause that much damage. Is that correct? No, it's not correct because, one of those gamma ray photons can cause a lot of damage. And what kind of damage do gamma ray photons cause? Well, let's take a look at the interaction of light and matter next. So what's the lowest energy electromagnetic radiation we're going to worry about? We'll put energy this way. As energy goes up, what happens to frequency? It goes up. So energy or frequency, they're both going to increase going up. What happens to wavelength? It goes down. So lambda is going to go down. as we go up. Lambda decreases. Well, we'll just go like that. And so the longest wavelength, shortest frequency, highest energy, or actually I shouldn't do that. The longest wavelength, long wavelength means low frequency. So the longest wavelength, lowest frequency, lowest energy light would be radio. And radio waves consist of oscillating electric and magnetic fields. So radio waves are typically characterized by their frequency. So like FM radio is megahertz or hundreds of megahertz. And so if we're at 100 megahertz, that's 100 million cycles per second. And so when a radio wave comes at you, it's oscillating at 100 million cycles in a second. That's extremely fast. It's extremely fast because it's moving at the speed of light. Radio waves travel at the speed of light. Radio waves and gamma rays travel at the exact same speed in a vacuum, speed of light. It's extremely fast, but it has a very long wavelength. It's 100 meters peak to peak. And that's 100 meters for one cycle. And so one cycle would be start at the top, and then 100 meters later, we're back. But it happens extremely fast because light moves very fast. So 100 meters wavelength gives you 1 million cycles per second. But anyway, 1 million cycles per second is considered low frequency. And so this is low energy light. And this low energy light, what can it do with matter? So this is light. And let's just see what the effect is on matter. So in the old days, you know what the radio antennas were made out of? Like if you see some really old cars, I don't think there are any old cars that have the pole antenna. Have you seen the metal pole antenna? And the electrons in metals are loosely held. And so if you have an oscillating field, which would be megahertz, then the electrons can oscillate at that megahertz level. And so what it does, radio waves do, is they excite electrons in metal. Metals have loosely held electrons, but plastics have tightly held electrons. So you don't see any cars, driving around with plastic co-hangers. You used to see, sometimes the antenna would break off and then they'd put a metal coat hanger to use as a substitute. But a plastic or wood coat hanger would not work because the electrons are too tightly held and they won't oscillate. Okay, what's higher in energy than radio waves? Microwave. Microwaves have enough energy to rotate small molecules. So if I look at a water molecule, one end is going to be negative, the other end is going to be positive. So the oscillating microwaves don't have enough energy to vibrate the bond, like I was showing earlier, but they have enough energy to rotate this molecule. So if it's positive, it flips one way, negative, it flips the other way, so it can start to rotate. And we end up with rotations. Rotate small molecules. Here's a rotating water molecule here. This is what we call the microwave spectrum for water over here. And, Infrared is higher in energy than microwaves. Infrared is enough to vibrate and so if we have infrared, well, one end of the bond is positive, the other end is negative. So that has enough energy to cause vibrations, vibrate water molecules. But actually, it has to be polar, vibrate polar bonds.
Does that also apply for the rotating and the microwaves? Does that have to be polar?
Yeah, it has to be polar. It has to be for it to interact with the field. Microwaves are kind of interesting. Let's go back to microwaves for a second. How fast does electromagnetic radiation travel? Travels at the speed of light. But inside a microwave oven, what you have is you have a standing wave. And so the microwave oven has microwaves here that are essentially stationary, the peaks and the valleys. And so we have a standing wave inside the microwave oven. And it's in phase like this. A microwave, do you know what frequency microwaves operate at? Microwaves operate at mu, this is the frequency, of 2.45 gigahertz. Giga is what? How many? Like a mega is a million, 10 to the 6. Giga would be a trillion. So it goes mega, million, and then what's a billion? So mega, and then what comes after mega? Actually, it goes mega, giga, like a megabyte, gigabyte, tera. And so actually it turns out giga is a billion. It's going to be 2.45 times 10 to the 9th hertz, which is 2.45 times 10 to the 9th cycles per second. But the cycles part is often left out, and they just say per second. A terahertz would be a trillion. What's the wavelength for a microwave? So the wavelength is C over nu. And so we'll plug in C, which is 3.00 times 10 to the 8 meters per second. And then the frequency is 2.45 times 10 to the 9 per second. And that's going to give me a lambda in meters. Can somebody calculate it?
How to 0.122 meters?
0.122 meters? Okay, thanks. 0.122 meters is 12.2 centimeters. So in a microwave oven, they have standing waves, and the peak-to-peak distance here is 12.2 centimeters. And so an interesting thing happens here. Since this is a standing wave, and we're going to have places where we have peak amplitude here and peak amplitude here, up and down. But there's going to be zero amplitude in certain parts of this. And so here we'll have positive amplitude and negative amplitude. Where we have positive and negative amplitude, there's power transmitted to the food. But where the amplitude goes through zero, there's no power transmitted to the food. And so what you're going to have is you're going to have hot spots and cold spots. Do you see that? The cold spots are going to correspond to these regions here called nodes. And so it's best if you can rotate the food in here. So if you have a turntable, the turntable is going to make sure that it's not stuck on a cold spot. You know, because you don't want parts of it frozen and parts of it hot. You're microwaving some food frozen. Or you just do it manually. You just move it so that you aren't. Or so that you can cook the food more evenly. You aren't doing something like this. But when we're at this non-zero amplitude, then it causes the water molecules to rotate, and that's going to increase collisions, and it's going to raise up the kinetic energy. In other words, it's going to increase the temperature of your food. We could also use infrared to warm it. So if I have a microwave, that'll warm up the food by rotating the water molecules like this and increase the kinetic energy. An infrared lamp will do the same thing. It will vibrate polar bonds like this. But the problem with water is this. There are only 3 ways in which water vibrates. And each of these 3 ways has a specific energy. These are called resonant frequencies or resonant energies. And if we don't have the right amount of energy, nothing happens. And so, for example, this type of vibration here, which is the symmetric stretching vibration, happens at 2.734 microns. Infrared's usually in wavelength units of microns. That's going to have a very specific energy. So if I don't have this much energy, this vibration doesn't happen. Or if I have too much energy, the vibration doesn't happen. It has to be just the right amount of energy. And that would be the resonant frequency for that. One way of thinking about it, this is not a perfect analogy, but, would be like a ship. If you have a giant ship here and there are small waves, are the small waves going to cause the giant ship to bob up and down, let's say a cruise ship? No. In fact, the cruise ship, you won't even notice these little waves here. And so those little waves aren't on the resonant frequency of the ship. However, if you have like a small boat here, this small boat will start to oscillate with the waves. And so that would be the resonant frequency. So it's a similar situation here. We just have to have the right resonant energy or the right resonant frequency or the right resonant wavelength to cause this vibration. And so if we have the infrared light source, then, and the infrared light source has a range of wavelengths, because infrared is what we call a band of energies, or a band of wavelengths, a band of light. Let me just show you here. And so if we have an infrared lamp that's shining infrared light over a range of wavelengths, these wavelengths here, then only one of these will cause that vibration. So that's a very sharp line here, corresponding to a very specific wavelength and a very specific frequency and a very specific energy. Then we have the bending vibration. These are long pairs here. The bending vibration, also very specific wavelength here. Only this wavelength is absorbed. So we're going to absorb 2.734 microns, 6.269 microns, and the asymmetric stretch here is is going to be at 2.662 microns. And so those are the only three infrared photons that are absorbed. So what that means is, if we're shining infrared light, we're shining this range of photons here, only three of those photons out of that whole range are absorbed, which means that all the other photons are not absorbed, which means we're wasting a lot of energy. So if we shine an infrared light here, it's not tuned to the resonant frequency of water vibrations. Whereas with a microwave oven, the microwave oven is tuned to the rotational frequency of the water. And so it turns out this frequency here is just the right frequency to rotate the water molecules. And therefore, we're not wasting a lot of energy. We aren't bombarding this with the whole range of microwaves. There's a wide range of microwave energies, which spans a wide range of frequencies. We're not bombarding the whole sample with that. We're just only hitting it with the resonant frequency of water rotation. And so microwaves are very efficient, because if we used an infrared lamp, that would be terribly inefficient because we're wasting a lot of the energy because it's just not absorbed. Does that make sense? And so this is why the microwaves were such a huge advance. The same thing here. You know, if we heat a pot of water over a flame, most of the energy is wasted because water only absorbs certain energies for the rotation and the vibration. And a lot of the rest of the energy is wasted. And so it's the same thing here. We're only hitting the resonant frequencies, that is, the energies that are perfectly tuned for that water. But once we go from infrared, then comes what? Visible light. And here visible is actually a very small part of the electromagnetic spectrum, but I'm going to expand it like they expanded here. At the low energy end of visible light is red light. And they have the border here between red and infrared at 760 nanometers. So we'll put that border in here. The border between red and infrared is 760 nanometers. Now, maybe some people can see all the way out to 760. Other people can't. You know, so it depends. And some people can't even see, much of red. They're maybe detecting over here. And so it's a little gray area there, but we'll just say that the edge of red is at 760. And then we use this acronym. We go red, orange, yellow, green, blue, indigo, violet. So red is the longest wavelength, lowest energy, lowest frequency. Violet's the highest energy, the highest frequency, and the shortest wavelength. And so that's going to be at about 390 nanometers. 390 nanometers is what we call the edge of violet. And then from violet, we go to what color? Actually, it's not a color. It's going to be invisible. But what type of electromagnetic radiation? Ultraviolet. I'm going to run out of room here. But ultraviolet, or UV. So visible light doesn't vibrate. It doesn't rotate. You know what visible light does? Visible light excites electrons in colored matter. So, if something's colorless, that means it's not absorbing any visible light. So this plastic, do you see this plastic is clear and colorless? It's not absorbing any visible light. But do you see this liquid? This liquid is blue. So if the liquid is blue, then that means it's absorbing visible light because it's making a blue color. Now, colors are generated in different ways. One of the ways color is generated is by absorbing all the colors except for blue. And so we can see that if we make the color wheel here, the color wheel is going to be like this, where we group indigo and violet together. And so this will be the color wheel. If we absorb all the colors except for blue, then it's going to appear blue. So one reason this liquid may appear blue is because all the other colors of the rainbow are being absorbed except for blue. And therefore we see blue because that's the only light that passes through, blue light. Another way that color is generated is by absorbing the complementary color. So if we absorb, let's say, orange here, then all the other colors average out to blue. So that blue color might be a result of absorbing orange light, or it could be a combination of things. So for example, if we absorb red and yellow, then it's going to average out to blue, or some other thing where we have multiple absorptions rather than a single absorption. And the reason it's absorbing those colors of light is because electrons are getting excited, and there's going to be what we call resonant frequency or resonant energy or resonant wavelength for the electrons too. Electrons, and it's like this ship here. If this were an electron here, it's not being excited by this frequency. But this electron is being excited by this frequency. It depends on how well that electron's anchored to the matter. Some electrons are very loosely anchored and they can be easily excited. Like, for example, in black. You know what's happening in black objects? They're absorbing all of them. And so all colors of the rainbow are being absorbed, it's going to appear black. Well, those electrons are being easily excited, in other words. White objects are going to pass all color. All these colors add up to white. All the colors of the rainbow. All right, ultraviolet excites the electrons a bit too much, such that bonds are breaking. And so this breaks bonds, like covalent bonds. And so electrons in a bond get too excited. Infrared just vibrates the electrons in a bond. Ultraviolet breaks the electrons in a bond. So it just breaks the bond. After ultraviolet comes what? X-rays and gamma rays. Okay, X-rays are lower energy, so X-rays, and gamma rays are higher in energy. Gamma rays here. And so X-rays and gamma rays, those not only break the bonds, but they can knock electrons off. Knocking electrons off we call ionization. So these are called ionizing radiation, and they ionize matter. That is, they'll break off electrons off matter. It's not that some of these, like visible light, can ionize matter. Like, for example, green visible light can ionize what? Like potassium metal. But green visible light is not going to ionize aluminum. The electrons in aluminum are held much more tightly. If you put aluminum into a microwave, do you know what happens? If you throw aluminum into a microwave, it shouldn't. When you put metals into microwaves, then those tend to ionize as well. There are other factors in there, not just this. Other factors being amplitude. All right, so this is a basic breakdown of gamma is this. This is the symbol for gamma. It's the lowercase Greek letter gamma. And it's spelled G-A-M-M-A, gamma.
And why? How we're talking about it has to be the specific wavelength for it to, move the boat up and down. kinetic energy. Why doesn't higher wavelengths? Why don't I get why it's the lower ones don't, but why does it have to be exact? Why doesn't the higher ones also?
For it, you can do it the higher ones. So for example, here, this is the photoelectron effect. If I hit this with green, and green's enough to eject the electron off here, what if I use violet? Well, violet is higher in energy. And so what violet does is it knocks an electron off and then kicks it off with more energy. And so here, the kinetic energy of the electron that's ejected is going to be a lot lower than the kinetic energy of the electron that's ejected here. So there's a mode for absorbing higher energies, but some things, there's no mode for absorbing higher energies. So for example, here, it's no problem because we can have any kinetic energy. We can have a little bit of kinetic energy or a lot of kinetic energy or anything in between. You know, it just changes the speed at which the electron's ejected. But there are some things that don't do that. So let's say I'm trying to jump over a gap here onto an island. If I'm trying to jump over a gap here onto an island, then I don't want too much energy because, yeah, I can make it over the jump, but I might miss the island here. And that's too much energy. And I don't want too little energy because I'm going to fall into this gap. And so in this case, I have to jump just with the right amount of energy. And so this would be the resonant energy here. I can't have too little and I can't have too much. This would be like the vibration of a water molecule. The vibration of the water molecule, I have to hit it on here. Because if I put too much energy there, there's no place to go. I can't do this vibration and then add a little bit of extra energy to make it go a little faster. It doesn't work like that. And so I have to hit it right on. And so in this case, there's a mechanism for absorbing a little higher energy. And so if this were the case, that is, this were a long platform like this, then I could hit it with just the right amount of energy or more. And it would just cause maybe a little faster vibration. But that vibration's already it, you know, and so we don't have any more here. And so what we have to do is we have to hit it just right. Sometimes we have this. This would be the, you know, there could be what we call overtones. These overtones are little islands here that would be, you know, higher energy where it can go. So you strike a note, it comes here, but if you hit a note, then we have a frequency higher that it can absorb at. And so it depends on what can happen with these vibrations. It's got to be right on. Otherwise, there's no other runoff room to go. Does that make sense?
Yeah. So if you have more energy and you have your water molecule and it's more than what you want to vibrate it in, you know, one of the resonance waves, it's just not going to do anything.
It's not going to do anything, right? And that's it's not going to do anything because there's no place for the water molecule to go with that much energy. And it's like this. If you tune it like this, like say you could change a knob here and that changes it, then eventually you'll see it'll hit here. But most of the time what we're doing is we're shining a photon of light and we're trying to kick it. And we're trying to kick it to hit this island here because this is allowed. And then if we kick it with too much energy, it goes here, but we can't adjust it. You know, it's not like, okay, if this were, let's say, if this were 121 kilojoules per mole's worth of energy, if this were 121 kilojoules per mole, but it only took 90 kilojoules per mole to make it here, I can't just go, I'm going to give it 90 kilojoules, make it land here, and then give it the extra 31 kilojoules, right? What I'm going to do is it's going to be kicked with 121 kilojoules, which is going to land in the wrong spot. If it lands in the wrong spot, nothing's going to happen because there's nothing there to absorb the energy. And so it's because we have to give it the full amount there. We can't just give part of this, is the way it works. It has to be given the full amount, and that full amount is not going to do anything. We'll see more of this. The photoelectric effect is different. The photoelectric, we have a minimum. And once we hit that minimum, then it ejects. We can go any amount over that minimum because all we do is increase the speed of the electron. And that speed can be any value. So, but most of the time it's not like that. And so the photoelectric effect we can go over. This wave analogy we can go over. You know, if this wave, if the boat oscillates with this wave, we can make an even smaller boat, and that'll oscillate. And so, you know, there'll be a certain, once we hit the minimum amount of energy to oscillate the big boat, then we can just increase it from there, kind of thing. You know, so it's a little different than what I'm talking about here. So we can see what these energies are. This is the infrared spectrum of water. And the wavelengths are in micrometers. They use something else here. These are wave numbers. Wave numbers are another way of doing energy. And so we're going from lower energy here to higher energy over here. And one funny thing about the infrared spectrum is that it's going to absorb only certain energies of light. Normally when we think of absorbance, we think of absorbance peaks. In infrared, it's inverted. And so when we're absorbing light, it's valleys. And so in the infrared spectrum, I see three valleys here. There's 1, 2, 3. And each of these valleys are going to correspond to a particular type of vibration. There are only 3 ways water can vibrate. And these are the 3 ways, according to energy. And so I can hit just one vibration and cause all the water molecules to vibrate like this. Whatever this is. I forgot which vibration this one is. Or this. Or this. Or I can shine a whole range of infrared energies and I'll get these 3 vibrations here. And so these are called absorption bands here. But these peaks here are nothing's happening. So water doesn't absorb any energies from 1,000 to 1,500 wave numbers. There's nothing. And so you're thinking, okay, this is the minimum. Here, why is it that when I add more energy, nothing happens? Because when you're adding that photon, it's too much, you know, cause it. We need just the right amount of energy to cause that vibration. Too little, nothing happens, and then too much, nothing happens because it can't absorb it. It's too much, and I can't split it. I can't split the photon in half and say, oh, don't take all of it. You know, so if 500 was enough, I can't take 1,000 wave number photon and split it in half and get it to work. It's not going to happen. And same thing here. Nothing happens here. This is a dead zone. And so it's either too much energy for these or too little energy for that vibration. There. It has to be just the right energy for this particular vibration to happen. All right, so that's a little bit about light. And what we're going to do is we're going to look at, or we'll think about sunlight. What's the sun made out of mostly? It's a plasma, and plasma is a partially ionized gas. What's the gas the sun is made out of? Hydrogen. In the sun, there's too much kinetic energy. There's so much kinetic energy that molecules can't exist. Molecules break apart. The covalent bond's too weak to hold it together in the high energy plasma of the sun. So we have hydrogen atoms in the sun. What do most hydrogen atoms consist of? Most hydrogen atoms consist of a proton and a electron. So if we think about the total energy of a hydrogen atom, what is the total energy of the hydrogen atom? Well, we got to think in terms of potential energy and kinetic energy. The potential energy of a hydrogen atom is the electrons held to the nucleus. You know, there's electric and electron, which is negative, and proton, which is positive. We're going to have electrical attraction there. In other words, a Coulombic attraction. And so to pull these apart is going to cost us energy. To bring them closer is going to release energy. So that's the potential energy. And then there's kinetic energy. Kinetic energy is these electrons are moving. And they're going to be moving with some kinetic energy. And people normally visualize this as orbiting. So we'll have an electron orbiting around the nucleus. Now, electrons' kinetic energy can be increased or decreased. If the electron's kinetic energy increases, then the electron's moving a little faster. And if it's moving a little faster, it's going to pull away from the nucleus. If the electron's energy decreases, it'll move a little slower and then be pulled into the nucleus. And so basically, this is different. What we expect here is we expect a continuum. A continuum means that any energy can be absorbed. So either the electron can absorb a little bit of energy or a lot of energy. That's different than what I was talking about over here. What I was talking about over here is something called quantization of energy, where it just has to be just the right amount, otherwise it's not absorbed. Here, this should be a continuum because I can add a tiny bit of energy, I can remove a tiny bit of energy, I can add a lot of energy, I can remove a lot of energy. In other words, I can just speed up or slow down the electron, cool it down, warm it up, that kind of thing. And so what we expect is a continuum. Now, in this continuum of energies, we can draw out a energy level diagram like this. So the electron could be here normally. Let's say the electron's down here normally. And then it could absorb a little bit of energy. It absorbs a little bit of energy. It doesn't stay excited forever. Eventually, it drops back down. So absorption, and then we have emission. And let's say the emission doesn't have to be in the same way. This one can absorb kinetic energy in different ways. The emission usually happens via light. And so when we emit, let's say we emit an infrared photon, there's conservation of energy. And so it absorbs a certain amount of energy, it releases a certain amount of energy coming back. Or it can go a little higher. If it goes a little higher, then what's a little higher in energy than infrared? Visible. So if it goes a little bit higher, it could emit a red photon. Actually, I don't know where to put my red pen. That's all right, I'm not going to do it in color. Red photon. And then a little higher, it could emit a green photon. And a little higher, it could emit, eventually a violet photon, right? And then a little higher, it could emit a ultraviolet photon. In fact, that's what we see from the sun. We see ultraviolet radiation, and then we see the full rainbow of colors. When we have the full rainbow of colors, what color is that? The full rainbow of colors will be white. So we get white light from the sun, and we get infrared radiation from the sun. And we get all those colors because we can excite the electron to any energy we want. And so, we get excited a little bit more, a little bit less, whatever. And so we get a continuum of light. This continuum of light is going to be white light. At least, that's what the part we see. The part we don't see, the infrared, we can feel it. You go outside, you stand in the shade, you put your hand out in the sun, you can feel it. We have an infrared detector, our skin. We can feel the warmth of the infrared radiation on our skin, right? You might be in the cool of the shade. Ultraviolet, you can feel that. If you get a sunburn, you can feel that. At least the effects of ultraviolet radiation. Hopefully we don't get too much ultraviolet. So we want the ozone layer to be intact to protect us from ultraviolet. Ultraviolet wasn't that bad many decades ago. You didn't get burned so quickly, but now it's pretty intense. All right, so it's just these excited hydrogen atoms. These excited hydrogen atoms are going to have excited electrons. And these excited electrons are going to not stay excited forever. Eventually, when they drop back down, they'll emit light. And in fact, they'll emit white light, and that's what we want, and that's what we see. And so what we can do is we can make a hydrogen lamp on Earth. Here. And so this is a tube, and this tube here is filled with hydrogen gas. And we're going to excite the hydrogen gas. We're going to excite the hydrogen gas by passing electric discharge through it. Electric discharge is like a lightning bolt. In fact, when you see lightning bolts, what color are lightning bolts? Lightning bolts are white light. And so all we're going to do is we're going to make a lightning bolt here under controlled circumstances with hydrogen. And when you look at that, does that look like white light to you? No, it's not white light. And so there's some kind of problem. Classical physics predicted we should get white light from a hydrogen lamp. Well, maybe it's not enough power. So I'll turn up the power on this, the voltage. You know what? Still not white. So I crank up the voltage. This is 5,000 volts, I think, or 2,500 volts. Still not white. In fact, I don't get white light. Instead, I get that weird light there. And what that weird light says is that this predicted white light from a H lamp, what was observed is only certain wavelengths of light. In other words, wavelength and energy are related. Only certain energies of light. And so what that means for the hydrogen atom is this. The hydrogen atom can't go any speed it wants. So for example, if I try to accelerate the hydrogen electron a little bit faster, nothing happens. It won't absorb. In other words, there's a forbidden zone. And so all this is forbidden. It's not allowed to be here. The next allowed one is out here. So what has to happen is the electron has to jump up to the next allowed one. And so let's say if the electron were at 10 miles an hour here. We can't accelerate to 11 miles an hour because that's forbidden. 12 miles an hour, that's forbidden. We'd have to jump up to 25. And at 25, that's allowed. And then you say, if 25 is allowed, then shouldn't 26 be allowed? No, 26 turns out to be forbidden. It's too much. It throws you into a forbidden zone. And then the next allowed is going to be out here. And so the question comes up, classical physics does not predict it. Classical physics predicted the electron should be able to take any energy it wants. It just can go faster or slower. And so modifications had to be made to classical physics, and we end up with quantum physics. Quantum physics says that we don't have a continuum of energies. The quantum means there are only certain energies that are allowed and certain energies that are forbidden. And so quantum adjustment is there are allowed and forbidden energies. And so what we do is we have unusual light patterns. These unusual light patterns aren't what we expect. What we expect is white light. What we get are weird. And so what we're going to do is we're going to analyze the light we get from these. And the way we're going to analyze the light is we're going to look at what colors of the rainbow are emitted. Are all the colors of the rainbow emitted? So if I go up to the LED light here, I want to shine light into this is where light enters our spectroscope. And so I'm going to point the square up at the light, and then I'm going to look to the side. So point the square up, and then look on the side and see what colors. And if I look at the LED, I see a rainbow of colors. We'll talk about LED lights later. But when I point this at the hydrogen lamp, I don't see a rainbow of colors. Well, instead, what I see are discontinuous spectrum of colors. And this discontinuous spectrum of colors is going to result in lines. And what we're going to do is we're going to just sketch out the line spectrum or the spectrum. Not all these are. And so hydrogen, the one we have on Earth here, only has 3 or 4 lines in there. And those lines correspond to specific energy or a specific wavelength in this case. And so the first step is we're going to calibrate our spectroscope. Some of these are easy to calibrate, others aren't. The way we calibrate it is by looking at a fluorescent lamp. And a fluorescent lamp is a discontinuous spectrum. Only certain colors of light are allowed. And so we're going to point the square at the fluorescent lamp, which is at the end of that bench. And then we're going to make sure it's reading at, there's a green line in the fluorescent light spectrum, and that green line should be reading at 546 nanometers. And so we can see, is the green line at 546? If it's at 546, then this is calibrated. If it's not at 546, we need to move the scale. That is this screen here. Some of these have a little hole where you can put a pencil in and slide it to the left or right to line up the green line with the 546 mark. Some of them don't, so some people use their finger. But this could be registering. So we can use the fluorescent lamp, or probably easier than using the fluorescent lamp is to use the sodium lamp over here. The sodium lamp has a very intense orange line. And it's actually what we call a doublet. There are 2 lines, but it's hard to see. This isn't very good because it doesn't show it. But it comes out about 590. So what we should see with the sodium lamp is one intense orange line at 590. Then you know this is calibrated. You can see it's probably easier than calibrating on the fluorescent. You can try calibrating on the fluorescent or the sodium lamp there. You might be able to resolve the 2 lines. It's called the sodium doublet. Let's see. But sometimes it's just hard to see. There are actually 2 lines there. Just looks like one line. Oh, this looks pretty good. This is most likely what you're going to just see. It's just one line at about 589, 590. Should be at 590. One line here. Then you know it's calibrated. One intense orange line. Well, the problem is there's a lot of light pollution in the lab, and so you're going to have light from different sources contaminating your spectrum. So when you're over there at the sodium, there's only one line in the visible, but other people are getting 5 lines. The other 4 lines are coming from light contamination from various sources. All right, so that's our lab. What we're going to do is we're going to take a look, what colors of light are we seeing here? And those colors of light are from exciting electrons and those exciting electrons dropping down. And we can't excite those to any energy. They're going to be resonant energies that they get excited to, and those are the only energies that they absorb.
So are those 2 with the continuum, are those wrong?
No, you're going to take this outside and look at the sun. Don't look directly at the sun, but you can look through this. And then we're going to see, actually, what we're going to see for the solar spectrum is a continuous rainbow. And so you aren't going to see any lines. You're just going to see the entire spectrum, red, orange, yellow, green, blue, indigo, violet. It's going to be continuous. When you look at the LEDs here, actually, the LEDs, I'll leave the lights on next door. You can go next door and take a look at the LEDs. When you look at the LEDs, what we see is a continuous rainbow of colors. And so it is correct the solar spectrum, and the sun consists of hydrogen atoms. The solar spectrum is a continuous. That is, the electrons can get excited to any energy. And so there's something not quite right with our picture. And so let me make a long story short here. The difference between our lamp here and the sun is that the degree of ionization. A plasma is an ionized gas. And this is what we call lower energy plasma. If this were like the sun's plasma, it would vaporize the glass here, basically. And so this is what we call non-equilibrium, non-thermal plasma. The sun is what we call thermal plasma, or it's closer to equilibrium. And so what the difference is, in the sun, there are going to be a lot of free electrons. So make a long story short, it's correct. The sun gives a continuous spectrum, but in the sun, we have free electrons. And if you have a free electron, the free electron can move at any speed it wants. And so the sun consists of free electrons. However, in our hydrogen lamp here, the electrons aren't free. There's very little ionization. There is ionization for sure because we got the lightning bolt going through there, although it doesn't look like a lightning bolt. But most of the electrons are not free. Most of the electrons are still attached to the proton. And so that's the big difference there. When we have a free electron, they can have any energy they want. When an electron is confined to an atom, it cannot have any energy it wants. But it's still against classical physics, because classical physics predicts that it just orbits a little farther out or orbits a little closer in. It should have a continuum of orbits available to it, but it doesn't. And what's the reason for that? Well, we'll get to the reason for that later, but for right now, we're just going to see the discontinuous spectrum of these lamps. All right, so the LED, we have an incandescent light here. So in the back, we have a fluorescent. This is a regular incandescent light bulb here. And then we have all the lamps here. We have hydrogen, mercury, neon, helium, etc. Sodium's over there. Okay, so the first, well, we'll be taking a look at the light with the spectroscope. But first, what we're going to do is we're going to weigh our samples. And so to weigh our samples, you're going to collect your samples from the oven and then cool them in a desiccator. You don't want to handle the crucibles with your fingers. One, they're going to be hot. But even after they cool down, you don't want to handle them with your fingers because you'll leave fingerprint residue. If you do handle them with your fingers, then wipe them off before you weigh them. And then we're going to weigh them in the balance room. After you're done weighing them, then you can handle it with your fingers. You don't need to clean the crucibles. You're going to return the crucibles, the beaker, the ribbed watch glass, and the weighing jar with your unknown sample back to the stockroom. And then we're done with that lab for the data. Okay, after we weigh these samples, then we'll start just observing the different light bulbs that we have in here with the spectroscope. And then it doesn't have to be accurate or particularly precise. One thing you try to get accurately is the single line in sodium, is that at 590. And the other thing is the hydrogen lamp. You know, there are 3 or 4 lines that you can see in the hydrogen spectrum, and those you want to write down. Some of these other lamps give you so many lines, it's too difficult to write them all down. All right, are there any questions?
So when you say you don't need to clean the crucibles, do we just leave
all the precipitate in there. Don't bother getting any of the precipitate out and just return to the stockroom with precipitate in there.